some philosophy. Let's start with some general philosophical principle. It's a principle that philosophers call reductionism. Reductionism is the principle or the philosophy that big things are made out of little things and little things are made out of littler things. That's one element of reductionism. How many people would agree with reductionism here? Yeah. I mean, you know, molecules are made out of atoms, atoms are made out of electrons and nuclei, nuclei are made out of protons and neutrons are made out of quarks and gluons, and so forth. I call that the building block theory, that houses are made out of bricks, bricks are made out of molecules, and nobody in their right mind mistakes a house for a brick. Right? We all know the bricks from the houses. The bricks are smaller than the houses. They're also simpler than the houses. So that's another element of reductionism. As you go deeper and deeper into the layers of reductionism, things get simpler, or at least we hope they do. That's a pious hope of reductionism. I think, from what we've learned, both from string theory, from the quantum mechanics of gravity, and so forth, that modern theories really do spell the end of reductionism. But before you end reductionism, it's interesting to ask how well it does as a philosophy and as a theory of elementary particles. If reductionism is right, particularly in that aspect which has to do with simplicity, as you go deeper and deeper, you might have expected that by now elementary particle physics would be pretty simple. We've gone several layers, and is it simple? The answer is no. It is very, very complicated, and to measure how complicated it is, you can simply ask how many different kinds of particles are there, and in particular, particles which are unexplained. Well, there's something like about 75 different particles, all of which, in the standard model of particle physics, maybe only about 20 or maybe even a little bit less than that independent particles that don't have tight relationships between each other. So it's maybe 10 to 15 or 20 distinct different particles, depending on how you count. How many parameters? Parameters, again, mean unexplained constants that have to go into the theory to make sense out of it. Well, about 20 distinct parameters, but the theory is definitely incomplete. We know that it's incomplete. It doesn't have gravity. It doesn't have dark matter. It doesn't have the particles that are necessary for inflation, the theory of cosmic inflation to make sense. And it has a terrible fine-tuning problem. We've talked about that fine-tuning problem, that in order to overcome this fine-tuning problem, people introduce things like supersymmetry. My guess is that supersymmetry will really be discovered at the LHC. But if it does, it adds about 100 new parameters. Well, I take that back. It's 100 plus n, where n is an unknown number, but that n is not zero because it's necessary for understanding the breaking of supersymmetry, why supersymmetry is not a real... another 100 parameters, a doubling of the number of all of the particles, plus a whole bunch of stuff that's necessary for inflation and other things. By the time you're finished, the standard model of particle physics, together with all of the bells and whistles that have to be added to understand everything, let's say, is a theory with about 200 parameters, a huge number of particles, and totally unexplained connections. So it's not simple. It's very, very complicated. And complicated So either you have to say, well, we haven't gotten anywhere near the bottom yet, or we just have to admit that maybe reductionism isn't working. But the idea that reductionism isn't working, that's not what I meant when I said modern theories sort of spell the end of reductionism. What I meant was a more theoretical fact. A more theoretical fact based on both quantum field theory and string theory. So I'll tell you a little bit about what is known. In particular, about the idea that endlessly, well, not necessarily endlessly, but that we can always tell the bricks from the houses. Is it really always true that we can tell which thing is more fundamental than which thing? I'm going to give you a couple of examples of places where in quantum field theory that idea has broken down badly. The first example was an example of a very simple kind. I'm not going to explain this, I'm just going to tell you about it. It was studying the quantum field theory of one-dimensional systems, models in which there was time and only one dimension of space. Very easy to draw, a dimension of space and a dimension of time, and that's all there is, and particles. What was discovered is that there's there are a number, in fact almost every theory of this type can be described in terms of particles which are fermions. Remember what fermions are? Fermions are particles that satisfy the Pauli exclusion principle. They're particles which have this odd behavior that they can't go into that you can't put two of them into the same state. Electrons are fermions, quarks are fermions, photons are not fermions, they're bosons. The opposite of a fermion is a boson. And all particles are either fermions or bosons. So in this mathematical theory,
are you a boson?
You start with some particles which are fermions.
I see you swimming around in there.
Fermion field, the object which describes the fermions, which creates and annihilates the fermions, we call psi.
There you are again.
Mathematical terminology is not important here. What is important is that the basic starting point is a field theory of fermions. Now, what happens if you put two fermions together? What do you make?
There you are again.
If you put two of them identical ones together, you make zero. But supposing two not quite identical ones, one sort of right next to the other, but not right on top of it, then you make a boson. Okay? For example, protons are fermions, electrons are fermions, hydrogen atoms are bosons. Okay? So you take a fermion and a boson, two fermions, and you put them together, almost together. Maybe there's some attractive force between them which holds them together. And these particles, which are now composites, they're clearly composites, they can move up and down. They're also particles, but they're composite particles. Those composite particles are bosons, and bosons are also described by fields. You would think that it's not really a fundamental field. You would think that it's a field.
Okay, I'm going to move to another slot, so if you come visit there.
Of the two particles stuck together, and you call it phi. Phi creates bosons. It creates pairs of these fermions.
There you go again.
That sounds very straightforward. But what was then discovered in these field theories is that you could rewrite exactly the same field theory in terms of an underlying starting point which started with the bosons. Let's draw that field theory over here. Now you start with the bosons. The fermions cannot be composites of the bosons because any number of bosons put together make another boson. But these fermions can be described in a totally new way. They're described through plot. This is not plotting time anymore. This is plotting the field phi as what's called a kink in the field phi. A place where the field phi smoothly jumps, doesn't jump suddenly. It smoothly jumps over a distance some distance, jumps from one value to another. It's called a kink. It's called a kink. If you want to picture it, I should have taken off my belt. Well, I won't take off my belt. But imagine my belt. Here it is. And here I've laid it out on the blackboard so that it's not twisted. That's got no kink. Now, take the belt and twist it. Rotate this end around by 2 pi so it's twisted once. It comes back to its original configuration over here, its original configuration over here, but in between it's twisted. That's a kink. That's a kink in my belt. I often do that. I often do that when I put my belt on and then discover 2 hours later when I'm talking to somebody that my belt is on wrong. Right? That's called a kink. The bizarre thing is that these fermions that we started with, the bricks which built the houses, the fermion bricks which built the boson houses, can now be re-represented as kinks in the boson field. Kinks which are extended, thick, and massive, much heavier than the bosons. Which are the houses? Which are the bricks? Nobody can say. It's entirely equivalent. There are parameters in such a theory. Field theories have parameters. It turns out that for some values of some ranges of the parameters, it's much more convenient to think of the fermions as the fundamental building blocks. And for another range of the parameters, the bosons are much more efficient at studying theory, and they are the more useful building blocks. It simply becomes a matter of which is more useful. Is it more useful to think of psi, the fermions, or phi bosons as the fundamental
focus on a different one, it comes into it.
And that depends on the parameters. That depends on a coupling constant. A coupling constant that's usually called G. It doesn't matter what it's called. So, starting with very small g, you discover that it's much more useful to think of the fermions as the starting point. Easy to deal with, easy to study. These things are composites that are held together by complicated forces. Now you start changing this coupling constant and increasing it and increasing. Oh, incidentally, when that g is very small, let's see, that kink is very tight, very small like that. Now you start changing the couple, and that's why the fermion is a small object. The fermion is a small object because it's a small kink. Now you start tuning the coupling constant, making it stronger and stronger. What happens is the kinks start to spread out. It gets less and less point-like, but the boson starts to behave more and more like a simple elementary object. So the question of which is fundamental and which is composite doesn't have a unique answer. By varying the constants, you can morph, you can make one thing go into the other, the house go into the bricks, so to speak.
How about?
That was a case that was known, oh gee, since I was a very young physicist.
There you come.
The key word is called bosonization. It's making a fermion out of bosons, or bosons out of fermions. All right, are there any things like this in elementary particle physics? It is believed that there are. And the belief centers around electric and magnetic monopoles. Let me tell you what an electric and magnetic monopole is. An electric monopole could be an electron, could be any charged particle, ordinary charged particle, surrounded by an electric field, usual electric field. And let's take the particle to be, let's say, an electron.
Well, that's not the one I was looking at, but you came into the one next to it.
It's very weak, as a matter of fact.
I was
It's a
looking
very
at this
weak
one.
electric charge. The
Can
amount
I
of
come
charge,
into that?
not just because the electron is small. That's actually not the issue. There's a dimensionless quantity. What's the dimensionless quantity called? fine structure constant?
Oh, the train.
The fine structure constant is a
And
measure
you're coming into
of
that
how
one.
much an electron would radiate if you
Harry.
accelerated
I
it
named you Harry.
or if you plowed it into a anode. If you plowed it into a stop, into a...
I think you're in that one.
how much it would
Definitely
radiate?
in that one.
How many photons would it radiate? The answer is that an electron will radiate on the average about 1 over 100 photons. Another way of saying it is the electron will only radiate about 1 out of 100 times when it stopped, radiate a photon. So the electron charge is very weak. And the electron is very simple. The electric field around it is rather weak because the electric charge is weak, and it doesn't do very much to the neighboring space around it. It doesn't polarize the vacuum. It doesn't create electron-positron pairs to any appreciable amount. Electron is simple. It is also believed that in nature
Photographing
they
is
do exist
all these little glass marbles.
Most physicists like myself believe
And you see,
magnetic monopoles.
I've got them on a kind of a stand that looks like a big old clothespin. And when you have the light just right, and you zoom up on the part of the marble that glistens, you get all this activity inside the shiny parts. And this little creature I call Harry, there he is again. It always comes. There he is.
Then waving around the bar magnet would look like
I think he likes his picture taken.
A magnetic monopole.
Don't know what he is.
Magnetic field comes out of the
A critter of light, I guess.
Exactly the same way
Creature
the
of the
comes
light.
out of the electric monopole.
Each of these
The monopoles that
gleaming parts of the marble has a different kind of design back of
a magnetic
it.
charge which is huge, very large. The force between two magnetic monopoles
I'll get
would
over on
be
this side.
10,000 times larger than the force between two electrons at the same distance.
Let's see if Harry comes to
That
visit.
means that the magnetic monopoles make large
See if he'll
fields
come visit
around
this
them
one.
and do very, very
Yep, there he
complicated
is.
things. Make a very
Hello,
complicated
Harry.
mess around them. That
How
complicated
you
mess
doing,
is
Harry?
extended.
Don't
It's
see you
broad,
real
the
good.
same
But
way that the
no,
kink
you're
was
there.
broad, and it's massive.
Oh
It's
boy,
very,
you ever
very
there.
heavy because there's so much going on in the vicinity of the monopole.
You're there. In all your
I'm not
glory.
really talking about the end of the bar
This is
magnet.
Harry.
I'm talking about
He's
the end of the bar
listening
magnet
to
without
this
the bar
physicist talk about the string theory.
They haven't been discovered in the laboratory because they're too heavy.
Maybe
to
they
make.
need to have a Harry
Will
theory.
they ever be discovered? Perhaps. But most theorists believe in them. But the point is, the more important point is, the mathematics of quantum electrodynamics, which contains monopoles and electrons, is totally unclear about which of them is the elementary particle. It depends on the fine structure constant. It depends on alpha, the fine structure constant. If the fine structure constant, which is basically the square of the electric charge of the